mic is muted.
Now can you hear me?
Yes.
Anybody out there can hear me besides the students in the room?
I can hear you.
Somebody
I can hear you as well.
Great. I have to guess. Okay. I want to continue these notes.
So
Thank
did
you.
you just turn your computer on? Because now it finally came up.
Okay.
You did, didn't you?
Okay. Yep. Okay. If you've got your notes, I'll be talking about the notes today. I can put those up on the screen for other people that are home. I'll say home, by the way. I'll quit apologizing. I have no idea where you are. I don't care. So I'll just say home. If you're in some floozy joint having a drink or something, that's fine too, but just don't probably put your sound on. Anyway, I don't even know what a floozy joint is. That's some word from the 1950s, okay? So, have no experience with such things. Okay, anyway, the curve stuff you've been seeing for some days. And so where I want to start just mentioning is the material on page 25 and 26. That you may or not remember, hope you do remember, in Calc 2, if you use this book, and this is trying to talk to everybody, if you use this book in section 8.1, page 584, the author had a little section on arc length. And that was where, at that time, we just were bringing that in. And so we took a parameterization of a curve. The curve sort of looked like a loop. And we said, okay, if that was a function of x, what would it be like? And we talked about corresponding, the f prime of x was capital Y prime of t over x prime of t and stuff. And then we talked about curvature, a second derivative. Anyway, that's back in chapter 8, section 1. And that is what I kind of reproduced on pages 25 and 26 of these notes. Okay, so the example 13.8 is like that example 8.1. I don't remember if it's exactly that, but it's like that. So I don't want to talk about that right now. That was Calc 2, but I just wanted to tell you that is there. Okay. Now, the next topic is page 27. And again, if you guys are home, I can bring that up. And for you at home, things were messed up here today. I got here an hour early, but it took me more than an hour to get things fixed up again. And so I'm a little bit late on setting up some of these files. And so you'll have to, I'll get one of these files set up here now, I hope. And as soon as I get that, it'll appear on your screen. I got to open it up first. Okay, now it's on my screen. Now I'll see if I can put it on your screen. Okay, so what should appear on your screen is the material I'm talking about. I just talked about pages 25 and 26. And so those of you at home or who have a computer here can see this is the stuff that's in chapter 8, section 1. So I'm going over that to get to the next thing, which is page 27, which is where I want to talk about just briefly a little bit. On 27, I hope you guys have read all this so I don't have to go through it, but there's a bunch of little definitions of what's a simple path and a closed curve and all those things. We're going to refer to these names. This is where they are. I'm just going to keep going here. Also, the direction of a path turns out to be the derivative of the function that describes the path. And that's on the next page, 28. And so the actual direction of the derivative is that vector multiplied by 1 over its length. If you remember how to normalize a vector is to make it length 1, and things in length 1 are directions. So the direction of the tangent vector is going to be the derivative of the function describing the parameterization, and the direction would be that same vector of length 1. That's on page 28. And so basically what we got to think about or worry about here are two different kinds of things. One is an arc, and the other is a closed curve, so to speak. Now, the idea of an arc is something that doesn't come back and join itself. Like a circle is not an, it's an arc, but it's a, we call it a closed curve because it comes back presumably and intersects. Now, suppose you go around a circle and keep going for another half circle. You couldn't see the fact that you went the extra half circle, all right? So that really wouldn't be the same curve because it's not closed anymore. If you don't end where you started, it's not closed. So a closed curve is where you end where you start. And an arc is where you don't end where you start, okay? And it turns out it's easier to play with arcs than it is to play with closed curves. Now, we are going to be later talking about solids and trying to do something with solids, like in 3 dimensions. Solids have surfaces. We're going to have to learn how to parameterize a surface. Surfaces sometimes have edges. Edges are curves. Okay, now that's if we're starting in 3 dimensions with a solid. So it's a surface is a 2-dimensional thing in 3 dimensions, and an edge is like a curve in 3 dimensions. That's like a 1-dimensional thing in 3 dimensions. Okay, and then you have vertices, those are points, maybe a vertex. That's where you have 2 things of 1 dimension coming together. Now, if we're starting out in 10 dimensions, that kind of solid in 10 dimensions will have a 9-dimensional surface and an 8-dimensional edge. And so the words don't always mean what they mean to us outside of math. Okay? The problem is we have to learn how to parameterize all of these different objects because we will later be taking a 3-dimensional solid and worrying about its surface and worrying about normal vectors pointing out of the thing like the surface of a sphere, and you might have arrows pointing out of the sphere. We'll have tangent planes. The tangent plane we can draw lines on. The lines have slopes. Anyway, so there's a hierarchy of stuff here we've got to keep in mind, and we'll be changing dimensions like n dimensions, n-1, n-2, depending on the kind of thing we're trying to picture. We won't be able to picture it if the dimension's too big. Anyway, now, again, what we learned back in Calc 2 was the length of a curve had to do with the integral of, you may remember the square root of the sum of squares. It was like 1 plus f prime of x squared, that integral. I'm in class here, I'm just pointing out, I'm just waving my hands for people. You guys who are at home can't see me waving my hands. Maybe that's a good, I guess you can, little picture. Anyway, what if the curve is not differentiable? So there's no derivatives involved here, okay? Or what about things at a corner? Corners are where you generally kind of think there may be some derivative problems, okay? Well, we need to talk about something called rectifiable curves. And this is on the notes, it's on page 28. And this is what we'll do here is define what we mean by the length of something where we don't necessarily have an integral and square root of sums of squares of derivatives of stuff. You may remember also we had an arc length. If we parameterized, it was the square root of the sum of the first function derivative squared plus the second function derivative squared. It was like x prime squared plus y prime squared, square root of that integral.
Hey, Dr. Brady.
Oh, that needs to be let in. Is that what you're telling me? Yes. Okay, let's see. Sorry, for you participants. No participants waiting. Message is Mitt. Mitt Marion. Oh, I have to do that. Anybody else? Just one? Okay, please sound off, you guys, if you know somebody else is waiting, because so we have 12, we have 10 people out there and 7 people here. We're missing about 5 people. They're going to miss a lot today. Life is the way it is. Okay, now I'm going to get off the written screen here a minute and go on the blackboard, but what you want to do to talk about a length is, if we think, and let me get off the blackboard now, or get off the screen here, you should be able, maybe, to see, just a second. Again, it's all was screwed up over the weekend. I guess you guys can see me now if you're home. Okay, so hopefully you can see the board. And I'm just going to like draw, a curve. I mean, it could be anything. Okay, we want to talk about how we can decide how long this thing is, and we will also assume we have a parameterization. So the parameterization is some kind of a function that, and we can use all kinds of letters. If I call it f for the moment, that, and if we call the parameter t, for each t, I get a point on the curve, as you guys all know. And for various t's, I get various points on the curve. We don't graph the function, we graph the range of the function. So if you can't see that at home, you need to tell me, okay? Now, how would we talk about the length of the curve? And the idea is to partition the domain. So what we're going to do is we're going to cut up the domain into a bunch of points. A regular partition would be cutting them all up so they are equal distance apart. But we wouldn't have to make a regular partition. We could just cut them up any way we want to. We would get a finite number of points, and you guys may remember from integrals and stuff, we usually call the first one x naught, and the next one x1, and then x2, and the last one we call xn. So when you partition, you get n plus 1 points. So if I cut this up into n intervals, I'll get 11 points because there's one more n point, and so on. That's all familiar. And then if we say, okay, what is f of x naught? That would be this point, maybe. This point here we would have as f of x naught. And then you would calculate where's f of x1. Maybe it's here. So this is f of x1. And what we're going to do is we're going to make a line segment between the two of them. We're going to do the same thing for all of them. So for whatever we have here, if I have a f of xk minus 1 and an f of xk, we'll have the line segment between those 2 points obtained from the partition. Now, that is what we call a polygonal line. Okay, it's a straight line in sections, and it's continuous because the end of the first one connects to the start of the second one, and so on. And so what we get is a line thing that follows the curve. Morning. Okay. This is and if we can take the length of points between points as a straight line distance. That's the square root of the sum of the squares and all that. So the point is, we can add up the norm of the difference. I'll get out of my own way here in a second. This is big enough for you guys at home. We can add up the norm of the difference of the points. And if we do that, we will get the length of the polygon. And it's not a closed polygon, it's a polygonal line. We'll get a length of lines here that connect at each point, and so forth. So this will be an approximation to what we're trying to find is the length of the curve. Now, we take every possible partition theoretically, and look at every possible sum. Okay? The least upper bound of those numbers, if there is one. So when you sum up these numbers, you get an answer. You'll get a approximate length. Then you take a different partition and you do it again. You get another approximate length. So we get a set of approximate lengths. If that set of numbers is unbounded, okay, in other words, if you can choose partitions to make the thing longer and longer and longer, then we won't have a length. It's going to be some kind of infinite length. Again, we're trying to decide what these things mean, okay? But if it's bounded, when you have a set of numbers that's bounded above, there's a least upper bound. That's a characteristic of real numbers. And that least upper bound is called the length of the curve. Okay? And further, we have more to say than just that, but I've got my own notes here, and I'm going to give you an example of a couple of things in a second. So what we have is called variation. And so from pages, I'm trying to see from pages like 28 of the notes at the bottom and 29 and so on, what I'm doing there in those pages is taking the old kind of thing we've done before, where we have a function of one dimension, not of several, and I have a curve, and I do the same thing. In other words, this thing I just did for several dimensions, I can do for one dimension. I can add up a bunch of things, again, the same way. And when at the bottom of, let's see, the top of page 29, we have, in the bottom of 28, we have what's called the variation, okay? And the variation for a one-dimensional thing, in other words, we actually have a graph, the summing up this idea gives me what's called a variation. Okay, that's on the bottom of page 28 of my notes. And we can go back to that on your screen in a minute. And if this set of things is bounded, then the function is said to be of bounded variation. And the least upper bound is called the total variation. Now, so that's discussed on page 28 and 29, and there's several different things there, and some theorems about such things, and page 30, and then we get to definition 1317 on page 30, which is what I talked about here that you guys looked at a few minutes ago. Now, do you not see me anymore? When I look at my own screen here, I only see my name. Do you guys see me walking around at home?
Yes, sir.
Okay.
Yes, sir.
What I did is I pinned that video. You can select a video and then click the pin video button, and that'll pull that up to that screen. So
Yeah.
at first it was just your name, but you can pin the video.
Okay. When I look, I've got your thing on right now, so I'm not seeing myself over there, and I was hoping you guys could. So anytime it blinks off and you only see my name, you need to tell me, because I don't realize what's going on. Somebody screwed with the thing over the weekend, and so I'm not trusting it right now. Anyway, the whole game for curves is going to be based on this idea of bounded variation. Now, what I want to do next is just put up on here, if this, you can see this, and I'm going to go over here. I think you can see where I am here better from home. One would be to consider the x times the cosine of, and you may remember last semester we talked about this kind of thing where it was the sine of 1 over x. Well, I want the cosine of pi over 2x. I want to consider this function. Now, you may or may not remember this. If you haven't had my class, we may not have looked at this kind of a function. This function is, if x is not 0, we want to define it to be x times the cosine of something. If it is 0, we want to define it to be 0. Now, you may remember, I hope you do, but if you don't, it's okay. What happens with the cosine is the cosine is never bigger than 1 and never smaller than -1. Now, so when I multiply x times the cosine, every time the cosine is 1, I'm going to go up and hit the x, because y equals x is this diagonal line. And every time the cosine is -1, I'm going to be down here hitting this one, the other line. So what happens when you try, if you would graph this on your calculator or computer, I hope you do, you will find out that you get this oscillating kind of thing that damps down to 0 because it's trapped between two lines. In this case, both of them 45 degrees, but two lines. So that's where, when we talk about limits of such things, we use what was called the squeeze theorem in calculus. Okay? And this same thing happens on the other side as well. All right? So you get this thing damping down on both sides. And the question is, if I go out here to x equals 1, so when the x on the function here, and this function is something where the parameterization, if I were trying to do curves, is on the x-axis. All right. So if I go out here to 1, I'll have a certain place on the curve, which is when x is 1, the cosine of pi over 2 is 0, and so on. Anyway, what I will get if I get this is this curve. The question is, how long is it? Is it of a finite length, using this idea of summing up polygonal lines? And I can show you that it's not a finite length. Okay, by how? Well, it goes back to the idea of you take a partition and you figure out the sum of the lengths of the lines between the points that you put on the curve. If every partition, when you get all of them, is a bounded set, that's when you get bounded variation, okay, and total variation. But in this case, I can pick a partition that gives me an infinite length. Now, it doesn't itself give me an infinite length, but if I pick the partition 1, 1/2, 1/3, 1/4, and so on, so 1 over n, if I pick that partition and stick those in here, okay, you get points on the curve. And then you draw lines. And we figure the length. If you guys work this out, you'll find out that the variation is 1 plus 1/2 plus 1/3 plus 1/4 plus 1 over n. In other words, this particular length of the line segments adds up to this harmonic, the beginning of a harmonic series. And if you remember our study about series, harmonic series diverge. So you pick a bigger n and you'll get more length. This turns out to be an example where the length here is infinite. Okay, that's one problem. Now, secondly, however, if you take this function instead with x squared, now the graph is going to be between two parabolas. And if you do this one turns out to have finite length. It's a bounded variation. Okay, and it doesn't seem like it's much different, but it turns out that it is. These functions we use to bring out the pathologies, the hard to understand stuff, okay, because they both oscillate up and down. But the first one that we talked about here is continuous at 0, but doesn't have a derivative at 0. Whereas this one has a derivative at 0, so it has at 0 it actually has a slope, okay, because it flattens out, and it turns out when it flattens out, it evidently affects its length. So I thought that might be of interest to you. That's not anything like anything in the book, because the book doesn't talk about this idea of rectifiable. Okay, now, so in the notes, and let me go back to those for you guys. Share the screen again for those of you at home. So in the notes, we talk about rectifiable paths and arc length. And as I say, this is based on the idea of adding up polygonal line segments and seeing for different partitions what kind of numbers we get. Now, that's not in the book at all, okay? The book does not discover, well, it doesn't discover, but it doesn't talk about this at all. And what we learn is, and it's the bottom of page 30, is a path is rectifiable. Rectifiable means finite length, roughly. A path is rectifiable if and only if its component functions are of bounded variation. In other words, when I have a vector valued function like I put up at the beginning, it has components. It's those component functions which may be of bounded variation or not, like the one I had on the screen, well, sorry, the one I had on the board a while ago, the x squared for you at home, you can't see it anymore, x squared cosine, whatever, that one turned out to be of bounded variation. If I had up a multi-dimensional curve with that as one component, and if all the rest of them were of bounded variation, then the curve I've got would be a wild one, but it is of finite length. Now, so that's what happens if all you know is that the curve is continuous, okay? In other words, don't know anything about derivative, don't know anything about corners and all that kind of stuff, just continuity. So what I'm doing, and the people in the class can't see what I'm doing here, I'm going down the pages, I'm on page 32 now, and we get down to the bottom of page 32, which says, let's suppose now that I have what's called a smooth path. Now, smooth means that the function f describing the parameterization is differentiable and the derivative is continuous, okay? So if we have a smooth path, if our thing we have, it has more properties, then it's rectifiable, meaning you don't have to go through all the stuff we did in the last 2 pages. It will be. I have a theorem about that. And the length is the integral of the norm of the derivative of the function. Now that's the same definition that you had in Calc 2, except in Calc 2 we might not have used the norm concept because, and I'm going to turn off the share screen in a second, if I have something like xy, then that integral becomes x prime of t squared plus y prime of t squared, because, so just a second. Let me turn off the share just for a moment. What's on the board now, I hope you can see. This is called the arc length. This is what is in the book, although again, the author is only talking about 2 dimensions or 3 dimensions, so he's going to write stuff like this. Okay, instead of norms of vectors derivatives, he's going to write the thing squared out, square root of the sum of squares. If I have 3 dimensions, I'd have another one. I'd have a z prime. I'd have a third component of my function. All right, so from now on to right now, we're back in what the author does in his text, because the author is always assuming that the functions we're going to be talking about have derivatives. But we will be later considering things where functions are curves, and we might not know whether they have derivatives or not. So we might have to consider the edge of something, and it may not be something we know about, so we might not know how to differentiate an edge function because we don't have the formula. I have a question in class here. Yeah.
The A and B, are those
that would be, that would, okay. What you have, if I have a curve, and I don't know if this is going to be big enough or not, but basically, whenever I have a parameterization, the A and B come from the domain of the things that you're going on. So if t is time, for example, you might be starting at time 0, yeah, but it might be something else besides time. We're going to find out. We're going to parameterize something by what we call arc length. We're going to use what we're doing to find the length. For example, we're going to use the idea, and I've told people in my classes before, when you're out on I-35 or any other road and you have trouble what people do is they call up a wrecker or something and they say, come to a certain mileage marker, because that is an identification of where you are on that road curve. And if you didn't have mileage markers, you'd have to describe so many miles from some town or whatever. But if you have mileage markers, and some roads now have mileage markers every 10th of a mile in the United States, which I think is kind of a waste of metal. But anyway, but it's measuring the length along the curve, and it's a wonderful way to tell people where you are. Okay. And also, if there's two cars in a caravan and you get apart, if you just know what mileage marker you are, you know where the other car is these days. In the old days, I remember sometimes when I waited on one side of a town and the other car was on the other side of the town, and we waited half a day because we wondered where people were and you didn't have any phones or anything. You know, let's meet at Keachai. Okay, well, that's fine as long as you know which side of Keachai and what road you're talking about. With phones and stuff, it's much easier now because you can actually call people stupid because you say, hey, I told you to meet on the north side of, you know. Anyway.
Well, now the turnpike, all the bridges are labeled to 1,000 foot a mile.
Yep. So, but that's ArcLink. That's using ArcLink to tell you where you are. And that's what we're going to be doing in a little bit. Okay. Okay. So, now, section 1.5 in the notes, that starts, and I can get these back on the screen in a minute. By the way, the rectifiable business, to prove it's the square root of the sum of square stuff, takes about 2 pages to prove. Okay. I put the proofs in there because I want you to see what's involved in all of this. But I mean, this stuff is not in the book. Okay. And so what I want to get to is essentially section 1.5, which in the notes is page 36. So let me go back to the screen here for you guys at home. I hope this is not too hard to follow along what I'm trying to say here today. Basically, on the bottom of, on 36, I'll find it in a minute. We talk about integration and differentiation. Now, in section 13.2 of the book, the author has a section on derivatives and a section on integrals. I consider that particular section pretty easy because you're given a function with several components. If you want to differentiate the function, all you do is differentiate the components and stick them in a vector. If you want to integrate the function, all you do is integrate every component and stick it in a vector. So I'm not going to concentrate on section 13.2 because I think you can read it and look at the examples and understand it right away. Okay, but I certainly would take questions for anybody that has such things. But I think that's the easy part. You know how to take derivatives, so just differentiate. Just don't do one. You have to do maybe 5 or something, or you might have to do 5 integrals. You know, but the concept is easy. So what we want to kind of concentrate on, and by the way, there's a fundamental theorem of calculus more or less for these kind of things on page 37. I didn't call it that, but it is. And what I want to get to is page 38 at the bottom, called regular paths. Now, what we have to start worrying about is whether going around the circle clockwise is the same as going around the circle counterclockwise. We want to distinguish between the two or say that's the same. And part of that has to do with whether or not we want to say what we're interested in is what points we get, not how we got them. You know, if I told you I'm rich, that means something, and maybe that just means how much money. You might want to know, how did I obtain my riches? Okay, because maybe I'm not supposed to be rich as a college professor, and if I am, maybe something else has been going on. You know, and there are people in the world who investigate, like if I suddenly make $1 million entry in my bank account, somebody might want to know, where'd that come from? Okay. And so there are some people interested with how you got it. And there are other people only interested that you got it. Like somebody might want to marry me if they know I have $1 million, And then they don't care how I got it, they just want to know that I got it. And, okay,
Put it
so
on
with,
the taxes, so you don't end up like out on.
with curves, it's the same way, okay? So we may just care about getting the thing and drawing it, or we may care about how we do it, like traveling along it, like in a race. We may care how many times we go around the oval in a race, because that makes a difference as to, a 500-mile race is a certain length that you have to achieve, but the racetrack may be only 2 miles around, and so you have to go around so many times, and it matters how many times you go around, okay? So anyway, and the other idea is what is about corners of pictures of things in multi-dimension, like 3 dimensions, that have corners. And there is a picture of a hypocycloid of 4 cusps in the text, okay? And you can go look and find it. It turns out that when you parameterize that, the derivatives all exist, even at the corners. And so the idea of a derivative, meaning you don't have a corner or a cusp, is lost when you parameterize, because when we parameterize, we're not looking at the graph of the function, we're looking at the range of the function. And it turns out that that changes things. So you can have a range that has corners, but the functions describing it don't, okay, are nice differentiable things. So sometimes authors argue about this, but the word smooth might produce a graph that has corners or cusps, okay? But the word regular means it will not have any corners or cusps. So on the bottom of page 38, I have the definition or the statement, the section called regular, because there are times when we need to distinguish between curves that have corners and curves that don't, and so forth. Now, the thing that characterizes a regular point of a curve, first of all, is the function describing the curve, and if you have page 38 there, that you can see, the function describing the curve is differentiable, and the derivative is continuous. That's the smooth part, okay? Now, if the derivative is never 0, then the curve is called regular. So at each point, you look to see whether the derivative is 0 or not. Now, one of the things we're going to do with curves is think of the t sometimes as time. And if the derivative is 0 at some time, we call that a stationary point, because the derivative is going to turn out to be velocity. And when the derivative is 0, the velocity is 0, and the velocity is 0, you're stopped, even if you're only stopped for 1 moment, okay? So when we interpret things that way, the derivative is going to be called the velocity, the second derivative is going to be called the acceleration, and that's going to bring up Newton's laws and a bunch of other stuff. That's the end of chapter 13. Anyway, if the derivative is never 0, that means you are traversing the curve without stopping, okay? Now, so that means for regular curves, if we talk about a race, for example, if you have people racing like a 100-meter dash, if you remember, or if you have horses racing, what happens in a horse race is they stick people in this strange-looking contraption, and the horse that they're riding in this strange-looking contraption, and they put them all on the same thing, and then this thing has gates, and the gates open and all the horses run out. That's the start of the race. Now, there's names for all this stuff, but the point is, what do you do when you are in a 100-yard dash? Everybody lines up and they maybe kneel down and all that kind of stuff, and they stretch and all, but they're all stopped when they start. When the gun goes off, hopefully not aimed at anybody, they all start running, okay? On the other hand, the 500-mile race in Indianapolis, they go around the track several times and get up to 200 miles an hour, and the race is started with all the cars going as fast as it can go at the beginning, which is why all the people who go to the race want to go to the first corner. That's a very popular place to be because it's the most dangerous place for the drivers on the first lap. And that's where all the wrecks occur, and that's what everybody goes to see. They won't tell you that, but that's actually probably true. Anyway, nobody wants anybody to get hurt, but if there's a wreck, they all want to see it. So anyway, the point is that's called a flying start in racing terms. Well, we can parameterize a flying start. We will not be parameterizing a horse race or a 100-yard dash, because in those curves that you make when you run, they're starting and a stopping, and that would be where the derivative is 0. Okay, so if I draw a curve on the board, and I can't do that right now to everybody at home, if I draw a curve on the board, I might go up to the board and start someplace and just stick my chalk on the thing and start up and draw a curve. But for our parameterizations, I've got to walk up and be moving as I move this thing, as I draw the thing. If you understand what I'm saying. So what we're going to parameterize is curves that are moving all the time. If you think of this as producing it in time. Okay? And that's because we want to talk about these norms, the lengths of the things in the denominator. When you make a direction, you're dividing by the norm. If that was 0, you're dividing by 0, which is not a good thing for finding finite answers. Okay? So because it turns out we want to have some denominators that aren't 0, we need to assume that the derivatives are never 0, which means we're never stopped in a drawing. So that's what we're going to be talking about. And the second thing is we're going to have to worry about arcs that are closed and arcs that are not closed. It turns out that closed ones are harder to deal with. So what I want you guys to concentrate on, if we like from page 39 on here, because that's where we're going to get most of the stuff out of this chapter. The author is always going to be assuming that the derivatives are not 0. He doesn't always tell you that. On page 39, there's some examples of things that don't look smooth and are and so forth, regular or regular not. That's just some examples. And so really what you get to quickly, I hope, is 41. What we want to talk about is when two curves are going to be considered to be the same. Okay? So what happens in a lot of times is you're given a function describing a curve. You're given a parameterization. Now, somebody, and we had an example that's the other day with cosine t and sine t. That produced a circle. It produced a circle starting at the x-axis and going counterclockwise around the circle. If we switch the sine and cosine to start with sine and cosine instead of cosine and sine, that turns out to do two things. One, it switches which way you're going, and also it changes where you start. Okay. Now, so when do we want to say that those two parameterizations produce the same curve, and when do we want to say they don't? That's the question. Okay. Now, for continuous curves, not regular curves, for continuous curves, we want to say they are the same if they produce the same trace, if they produce the same picture. But for regular curves, we bring in derivatives. We want to distinguish between something going clockwise and something going counterclockwise. We want to distinguish on a closed curve. We don't want curves to be the same if they start in different places and things like that. So the regular curves, we get a lot more sticky about it, because one of the things we're trying to do is to get a good feeling of the length of a curve. And if you draw a circle and go around it twice, you get a trace that looks like you went around it once. If all we're concerned about is the trace, then it doesn't matter which parameterization you use. Okay, on the other hand, if we do worry about the length of that, see, we want the circumference of the circle to be what you get when you go around once. not when you go around twice. So when we're worried about zeroing in on what the length of something is, we have to be much more specific about what we allow to parameterize the curve. So we have to decide when our two parameterizations give us the same length, for example. And so what is involved is what are called parameter changes. Now I'm going to, again, and we're running out of time, it's 18 after, so let me not do that. Basically, what happens with this idea, well, I think I will get off here. Okay, so you guys should be studying the next 9 or 10 pages, 40 to 50 for Wednesday. But let me just real quickly say something on something you can see, I hope. So if you can see me again, I hope you can. Trying to see here what I can say here fast. If I have a curve again, and I have one parameterization, so that would be like a function f. And suppose somebody else says, hey, I got a better way to do it. And so they have a parameterization g. Okay, both of them draw the curve, but they start in a different place. They may have different things, like we said the other day, cosine, sine, and sine, cosine. Now, I'm talking about the arc now, not a closed thing yet, just because I chose to make it open. Okay. Anyway, what you want to know is whether or not there's a relationship between the two intervals. Okay. So if there is a function phi, and if I call things over here s and call things over here t, just for purposes of the 2 minutes or less, I don't have any more. Okay. For every s, there is a t. Okay. Now, if so, this function, and let me go over here real quick. This function actually would be something we're used to seeing because we have two intervals. And if I'm trying to go from one place to the other, you're used to doing that in an XY situation, where for every s here, there would be a t. So right now I'm on the st axis instead of the xy axis, but I'm hoping you're understanding that idea. So for each point here, there's a point here. So what I get is a curve between the two intervals. Okay. Now the one I drew here is increasing. Or to put it differently, the derivative is positive, maybe, if it's a derivative. So what we say is we have a continuous parameter change if you have a function between the two that's continuous. You have a differentiable parameter change if, for example, that you have a curve description here is this. Now, when do we say the two things are the same? Well, if I start here and go over here and then go up here, if I go that way, is that the same as going directly here? If it is, then they are equivalent. They're related. In other words, if going through this process over here and here gives me the same point as, in other words, here, if this is g of s, and it's also f of phi of s, if it's both at the same time, that's when the curves are equivalent. Okay, that's when we say the two parameterizations are equivalent, where we get the same curve. So it all has to do with the nature of being able to get a relationship between the two domains that define the two curves. And so I'm hoping that that's enough. There's 21 after, but I'm hoping that that will give you enough to read the stuff. But there's a difference between an open arc and a closed curve. And there is one question here. I'm going to stop the recording here now.